Okay, so let's get into simplifying radicals. So a couple of things we see we actually kind of done separately in the previous sections. We just haven't explicitly spelled them out. And so right here, I have two separate radicals. And so what I'm able to do in this, it doesn't matter what's under the root in this case. It matters that the root is the same. So if the root is the same, like a third root or a fourth root, then what I can do is I can multiply the things under the root together and take the overall nth root. So that doesn't seem like super advantageous. Like in this first example, we have root 5 times root 7. Well, that gets me root 35, which honestly isn't really a whole lot nicer than what I had before. There's not really a nice root of root 35, but that's not always the case. So in the next example, I have the cube root of 2 times the cube root of 4. Now, individually, those are not very nice numbers. You're going to get some sort of decimal. But since they have the same root number, they're both cube roots, well, I can multiply the things under the cube roots, 2 times 4, which will get me 8. I take the cube root of 8 and I get 2. Similarly, and like I said, we've definitely seen this before. If I'm taking the root of an entire fraction, I can break it up and take the individual roots, and vice versa. And this goes for the previous slide too. That if it helps me and I have two separate roots, then that might not be really able to, that might not help me solve my equation at all or evaluate my expression at all. I can combine them and put them into a single root. But again, their roots have to be the same. So to see that in practice, here I have two cases where it's nice to break things up. Square root of 36 over 49, I can break it up into two separate roots, and I get square root of 36 is 6, square root of 49 is 7, so I get 6 over 7. And now I take the fourth root of this entire fraction, so I can break it up into two different parts. There's really not a nice fourth root of 5, but there is a nice fourth root of 81x to the 8th. And so the fourth root of 81 is 3. The fourth root of x to the 8th is x squared, because 8 divided by 4 is 2. But like I said, sometimes it's better to go in the reverse. So if I have two separate things that might not seem like actual square roots, I can combine them into a single thing, and maybe that division will make it so that I can have something nice to simplify. And so what this really is leading into, I mean, there is value in knowing both of those things, but we like to kind of simplify radicals sometimes. So even though we might not get a nice straight up answer, we can make radicals a little bit nicer than in their current form. So as kind of a hopefully review, but maybe not, maybe you haven't seen factor trees before, we're going to talk about just factor trees, not even simplifying radicals yet. And so if I'm doing a factor tree of a number like 28, I have to pick two things that multiply to get 28. So maybe there's more than that. In fact, there is more than that, but I'm picking 2 and 14. I believe you could pick 7 and 4. There might be another thing, but I think that might be it. So your tree might look a little bit differently, but kind of the result and all that I'm concerned about in the tree is going to be the same regardless of what you pick in this first step or really any step. And so the only two things that multiply to 2 are 2 and 1. We don't really count 1, so we're just going to sit with 2 on the left side. And on the right side, I have 14. Okay, well, 2 times 7 gets me 14. And again, I can't break up 2. There aren't two things that multiply to get me 7, so that's it for that factor tree. We could even have a bigger factor tree. So I have 162 here. And again, there's probably a clever choice of two things that multiply to get me 162. But why not 2? It's even, so I know 2 works, and then I just have to divide 162 by 2. So I get 81, and then I break that up. 9 times 9 gets me 81. 3 times 3 gets me 9. 3 times 3 gets me 9. And so that is the factor tree for 162. That is a factor tree of 162. And so now that we kind of have two examples, what I was talking about, that if you did this in a different way, you pick different numbers, then the very last number that you have, like I have 4 3s and 1 2 on the right side, and I have 2 2s and 1 7 on the left side, that would be the same regardless of how you break down your tree, and that's all we really care about when we're using this factor tree to simplify roots. So let's get into it. How we do it is we have to look at the root that we're dealing with. So if I'm trying to simplify a cube root, I am going to look for groups of 3. If I have a 4th root, I'm going to look for groups of 4. If I have a square root, I'm going to look for groups of 2. And I'm looking for, in those, we call these kind of leaves, the bottom parts of my tree. So the right side, I have 4 3s. So if I was looking for a 4th root, I am looking for 4 of a kind, and I have that. So let's see that in an example. I have 72 here. I can do 8 times 9 gets me 72, certainly. Again, there's other things I could pick, but that's what I'm choosing for now. They definitely multiply to get me 72. I'm going to break up my 9 into a 3 and a 3. Break up my 8 into a 2 and a 4. And then 4 breaks into 2 and 2, 2 times 2. And so now that I'm dealing with a cube root, I'm looking at my leaves and I'm saying, okay, do I have any 3 of a kind? I do. I have 1, 2, 3 2s. And so that guy, what I do is I kind of bring him outside of my root. So when I get done with this process, I'm going to have a 2 in front of a cube root of something. So to determine what that something is, I take my remaining things, the stuff that didn't pair up, or like it was a 3 of a kind or a 4 of a kind or whatever, depending on the root that you have, and I put them on the inside of my root. So one big difference here is that the 3 of a kind that I had, I only use one of them. So I had 3 2s, but I pulled him outside of the root, and so to compensate for that, I only am going to use one of them. And then my leftovers, the things that I kind of squared in purple, that is going to be inside my root, and I just leave them. I don't only use one of them. I'm going to leave both of them. And then I multiply. 3 times 3 is 9. Oh, I guess I didn't write it. So my final answer would be 2 cube root of 9. Now, using the factor tree from 162 from the previous example, yeah, I'm kind of sprinting through the factor tree. That's because we already did it. So we did this on the previous slide. You can rewind a bit if you want to, but this is a factor tree of 162. And so now I'm dealing with a square root. So I'm looking at pairs on my leaves, not the fruit, pair of numbers on my leaves. And here I have, oh, there we are. There's the 2 cube root 9. And here I have one pair of 3s. I have another pair of 3s. And so, and then I have my 2 kind of left over that doesn't match up with anything, unfortunately for him. And so since I have 2 pairs of 3s, I bring 1 and I bring 2 and I put that in front of my square root. So honestly, generally how I write this is when I find that first pair, I throw it right in front of my root. And then if I find another pair, I throw that right in front of my root. In this case, we just did that in one step. And then I have the 2 kind of left hanging out there. So I do 3 times 3 gets me 9, root 2. Pause for a second. Okay. Now, if we're dealing with just straight variables and powers, it seems weird, but we actually do the same thing. We're looking for groups of 3. We just have to be careful about how we're looking for them. So I have x to the 8th, which means that I have a total of 8 x's. So if I'm dealing with a cube root, I want to look for groups of 3 x's. So, well, okay, instead of looking at my expanded 8 different x's, I can see that if I pull 3 x's out, then I'll be left with x to the 5th. I can pull another 3 x's out, and then I'll be left with x squared. And so that's how I can group things up. I have I have x cubed times x squared. So I would pull out 2 of those x cubes, leaving me with x times x, and then that x squared is unfortunately left behind. And so x times x is x squared, cube root of x squared. So if we have something with a number and we have a variable, we kind of just treat it as, oh, it's like 2 separate problems. So we start with just the numbers, make a factor tree for 36. 6 times 6 is 36. 2 times 3 gets me 6. 2 times 3 gets me 6. I have a square root, so I'm looking for pairs. I have a pair of 2s, and I have a pair of 3s. So in this case, I actually have nothing left over. And so if this was just the square root of 36, I would just call it 6 and kind of let go of my square root. Here we have a few more things going on, but that can happen, so just be aware of that. So I know that I have a 6 in front of my square root. Well, I know I have a 2 and a 3, and well, 2 times 3 gives me 6, so I know that's happening. And then I have a total of 5 x's. So I'm looking for groups of 2 in my x to the 5th. Well, I can pull out one x squared, leaving me with 3 remaining x's. I can pull out another x squared, leaving me with a single x. And so that's how I get that x squared times times x. So it's that process of kind of like digging the right amount of items out of that variable until we can't find that amount anymore. And so I pull out those two x squareds, which would be x times x, giving me x squared, confusingly enough. And I bring them in front of my square root, leaving behind that lonesome single x. And so I get a final answer of 6x squared times square root of x. Ooh, all right, got another big one. This one's got 3 things going on, but it's not that bad if we kind of just go step by step and treat it as 3 different problems. So starting with 32, factor tree, I get 16 times 2 gets me 32. 4 times 4 gets me 16. 2 times 2 gets me 4. 2 times 2 gets me 4. So I'm looking for pairs, and I have one pair of 2's, another pair of 2's, and then I have this unfortunate 2 left behind. So I know at the very least I will have a 4 in front of my square root because I have one pair of 2's, 2 pair of 2's, so 2 times 2 gives me 4. And then I have a lonesome 2 left over. And now I would have kind of already done this in the step as I've broken up what I was looking for with my variables. So looking at my p's, I have 4 of them. So I can pull one group of p squareds out of it. I can pull another group of p squareds, and then I'm actually left with no more p squareds, which is fine. So I'm going to pull out 2 pairs and put them in front, so I will have 2 p's in front. And then I move on to my q's. I have a total of 7 q's, so I can remove 2 of them, and then I'll have 5 q's left. And I can remove 2 of them, and then I'll have 3 q's left, and then I'll remove 2 of them, and I'll have 1 q left. And so that's why I have those 3 groups of q's squared. So pulling out the 2 pairs of p squareds get me p squared. Pulling out the 3 groups of, or the 3 pairs of q squared, 3 pairs of q, so 3 q squareds. I'm left with just q to the 3rd, and then whatever's left over is just the single 2 and the q. Now, this is, okay, I did go over it, that's good. In this case, I'm kind of going backwards from the division. So we saw earlier in this lecture that sometimes if I have 2 things being divided, it's good to break it up into 2 separate pieces and then take the square root, but that's not always the case. So these are both good examples of, if I see root 80 over root 5, well, I can make that one entire square root and just make it 80 over 5 square rooted. And 80 over 5, very coincidentally, not really coincidentally because I made the question, but 80 divided by 5 is 16. And so the square root of 16 is something we know, it's 4. I don't know if I wrote it out, I guess I didn't. But the square root of 16 is 4, and so that's what we get. We get a nice whole number instead of dealing with 2 radicals and we're dealing with fraction that we initially had. And so that's always an option. Sometimes it's better to break things up, and sometimes it's better to push them together. And that's what happens in this next question. I have a 5 times the cube root of 40 times x to the 5th, y to the 7th over the cube root of 5y. I somehow abandoned my 5 in front of my entire root, so that's a mistake, but doesn't really affect the question. And so now I'm going to try and push everything together, make it a single fraction, and hope that that makes my life easier. So now I have a single fraction. 40 divided by 5 is 8. X to the 5th, there's nothing to divide, so it just stays x to the 5th. And then y to the 7th over y gets me y to the 6th. And now, and generally this is what happens when we're dealing with a lot of variables and roots of the same number, now I have something that I can simplify. I can kind of remove stuff from inside of my root, move it to the outside to make my life a little bit easier. So I'm starting with my 8s. It's 8, 2 times 4 is 8, 2 times 2 is 4. Cube root of 8 is, 2 times 2 is 4. And so now I'm looking for 3 of a kind since I have a cube root. Well, I have 3 2's right here. So I'm going to remove that from my entire root. And then we go back to the game of playing when we're dealing with the variables of if I'm dealing with something to the third root, I'm looking for groups of 3's. So if I have 5 x's, I can pull out one group of 3 from that and that'll leave behind an x squared. And that's it. I can't go further. And then I move to my y. I have 6 of them. So I can pull out one group of 3 and I can pull out another group of 3. And so now with that in mind, I see that I have a cube root. So I can pull out one group of x cubed in front, just leaving me with 2x. And then I can pull out my 2 groups of y cubed, which leaves me with a y squared in front of my root. And then the only thing left is my x squared under my cube root. Now, what I've lost in kind of this whole mess of things is back in B at the very beginning of my question, I had a 5 in front of my cube root. And so he actually would not have come into play until maybe the step before the last step, but really the last step. And so I should have a 5 times this entire thing. And if that's the case, well, I would just simplify it. So I would do 5 times 2xy squared, which gets me cube root of x squared. So my final answer should be 10xy squared cube root of x squared.